Cambridge University. So she's going to talk about cosmic ray diffusion in supernova remnants.
Thank you. Thank you for having me here today. It's really an honor to be here. And today I will be talking about cosmic ray acceleration in supernova remnants. So cosmic rays have been Again, it's an honor to be here, and today we're talking about cosmic ray acceleration in supernova remnants. So cosmic rays have been puzzling researchers for over a century. In the early 1900s, they were both tried to take a micrometer on top of the Eiffel Tower, and it wasn't until the 1912 that Victor Hess took electrometers on top of balloons and discovered cosmic rays and found them coming from above rather than from below. So today what I'll be talking about is the diffusion coefficient. The diffusion coefficient, of course, relates the velocity into the time derivative density distribution function. And if you change the diffusion coefficient, can you accelerate cosmic rays to higher energies? It's a puzzle as to how you can get cosmic rays at the energies observed on Earth. So my collaborators are Paul Edmond, who's at CITA in Harvard, Jill Perron, who's also a National Fellow at the University of Manitoba, and Professor Silver Hart at the University of Manitoba, and Professor Yoshua at the University of Manitoba. And I'd like to acknowledge our founding CITA and starting the CRC programs. So I'd like to emphasize that these are very preliminary studies. I've been working on this for less than a year, and I've discovered it to be a very beautiful and interesting subject. So I'm very happy to be working on it. So the takeaway message is that diffusion coefficient affects the energy reached by cosmic rays. The Bohm assumption is the assumption typically used for the diffusion coefficient, which explains cosmic ray acceleration only up to 10 to the 14th eV, and it's thought that cosmic rays can come from supernova remnants to up to the knee or 10 to the 15th eV. Another takeaway message is that Bohm diffusion and Bohm diffusion coefficient is only an assumption. Can we explain the energies of cosmic rays found on Earth at least up to 10 to 15 eV in another model? And we're discovering that solving this problem is a computational challenge.
Sorry about the cameras.
Oh, it's great.
No, I think some. It's like construction cranes. Oh, is it?
So I'll first begin with an introduction introducing cosmic rays in supernova remnants. Then I will discuss the MHD code format that I'm using to examine this problem so it combines maximum equations with hydrodynamics. I'll discuss different diffusion coefficient models, Bohm diffusion plus a possible alternative model, and this can be explored further. I'll discuss results from our toy model. We've been running Wombat and with unrealistic parameters just to get it running and to test it, and this I'm calling the toy model, so I'll discuss those results. I'll discuss the current work, which is using more physical parameters, and finally we can conclude with future work that we want to do on this subject. So first I'll begin with an introduction of what are supernova remnants. Supernovae eject supersonic shells of material that sweep off the interstellar medium and drive a shockwave. The shell is a supernova remnant. There are three phases which occur in supernova remnants, and the time scale depends on the ambient density, energy, and mass. So the first phase is free expansion, in which the ejected dominates over the swept-up mass. This lasts approximately 200 to 300 years. The second phase is the adiabatic, Taylor set-off phase, and in this phase can last up to about 20,000 years and reaches a radius of 20.5 parsecs approximately. The third phase, which is also dominated by the swept-up mass over the ejected, is the radiative phase, or the snowplow phase. And in this phase, you have radiative cooling, which goes to ISM, and it can last up to 500,000 years. It's a pressure-driven expansion, so the pressure inside is greater than the pressure outside. And once again, you have more efficient cooling. So there are two types of shocks that occur in a supernova remnant. There's the forward shock, shoots up the ISM, and the forward shock goes into the ISM. And there's a reverse shock, which travels into the ejecta from the outer layer. This heats up the ejecta. This is an image of Tycho taken by Chandra. You can see the shock front is on the outer, the bluish outer edge, and the synchrotron radiation is in this area as well. And because there's evidence of synchrotron radiation, there's evidence of accelerated cosmic rays, accelerated particles. So here is a sort of inside picture of supernova remnants. You have the area which is the shock ISM, and there's a forward shock. And this area is the unshocked ISM. This is in the rest frame of the shock. In the interior, you have the unshocked ejecta, then you have the shocked ejecta, and then contact continuity is the boundary between the shocked ejecta, and the shocked ISM. And this area is known to be hydrodynamically unstable. So here's an introduction to supernova remnant Tycho. The iron emission lines are the red areas in here. The green is the silicon emission line. The blue is between 4 to 6 kVs here. And again, what we're interested in is this limb, which has evidence of synchrotron radiation. And the shock front is the bluish purplish area, which is inferred to energies of 160 V. So the model of the supernova remnant is that it has an explosion energy of 10 to the 1 Earth, and then a core collapse supernova would result in an ejected mass of up to 10 solar masses. Using the Bohm limit, you can explain galactic cosmic rays with a power law reaching to 10 to the 14th degree. The model is that cosmic rays take in about 30% of the explosion energy, and galactic cosmic rays are thought to come from supernova shocks. The energy input from the supernova to the ISM can be 10 to 42 Earths per second. The power law for synchrotron spectra is expected given the cosmic ray spectrum. So the composition of cosmic rays is they originate either from the sun or distant places in the galaxy. And 99% are thought to be from nuclei, 90% of those being hydrogen nuclei, 9% helium nuclei, 9% from elements, and 1% of cosmic rays are thought to be from electrons. So this is an image of the Crab Nebula, which is a supernova remnant, which is also a Serpent nebula. So now we'll introduce cosmic rays. Victor has discovered cosmic rays between 1911 and 1913. Cosmic ray production is thought to occur in supernova remnant shocks, SP accelerators, active galactic nuclei, and interplanetary shocks. And the Committee on Physics in the Universe's address to the National Academy of Science posed the question of the origin and transport of cosmic rays as one of 11 major questions to be answered in astrophysics. So I've been working a little bit on cosmic ray transport and diffusion coefficients in some other papers, and we're discovering that there's a lot of discussion about this. You know, what is the cosmic ray transport equation and what is the diffusion coefficient? So there's a lot of discussion about what the correct equation for the diffusion, what the correct diffusion coefficient is. So in 1995, Craig published in Nature evidence for shock acceleration of high-energy electrons in supernova remnant SM1006 using the ASCA X-ray observatory. They looked at emission from remnant shell edges and found that to fit a power spectrum, they found that there's non-thermal, they needed non-thermal synchrotron radiation to fit the power spectrum, in which electrons would be accelerated to 100 eV. It is assumed that there's also proton acceleration. And the lack of emission lines in the spectra was also some evidence for cosmic rays. In 2004, the HESS collaboration found TeV range gamma ray spectrum of efficiently charged particles consistent with supernova remnant theory. So this is a picture I got from Wikipedia. I think it's from NASA. Of the flux of cosmic rays versus the energy in the water plot. So you can see at low energies you have a large flux, a large number of cosmic rays per area, and at high energies you have not as many cosmic rays per area per time. And this is the mean, which is about 10 to the 15 eV. It's thought that cosmic rays are produced in the same sources below the mean and above the mean, and the mean is sort of the area where there might be differences in where they come from. So it's thought that supernova remnants can accelerate cosmic rays up to the mean. So the questions of interest in cosmic ray physics are: what are the maximum accelerated energies of cosmic rays? What is the cosmic ray acceleration efficiency? Is there a presence of ion acceleration in the shocks? Again, there's questions of cosmic ray propagation. The role of the diffusion coefficient. How does the diffusion coefficient affect the acceleration efficiency and maximum energy reached? And the role of shock geometry. So if you change the relationship between the shock and the magnetic field, can you get higher accelerated particles? So there's different codes that we're going to be using and that we are using to explore this issue. We're using Wombat, which is developed at the U of N and at Minnesota with Paul Edmund, and this is an MHD code. And Marcus, which was developed by Nicolas and Gilles Ferrand. The difference is that Wombat uses a lot of different modules and can solve a lot of different problems, whereas Marcus is more designed, I think, to tackle this problem, but Marcus does not include the magnetic field. So how can you, what is the theory that would allow you to accelerate particles to such high energies? Well, what's thought to be the theory is diffusive shock acceleration, which is where the particles from the unshocked region bounce back and forth across the shock from the unshocked upstream to the shock downstream. And it's this crossing back and forth of the shock and the rest of the shock that can accelerate the particles to such high energies. You can also have the particles scattering off of the turbulent magnetic field lines. And this can also give you an acceleration of the particles. So shock is a discontinuity over a finite thickness, and it obeys the flux conservation laws, which stays at the jump shock conditions, where rho is the density, v is the velocity of ambient material, and p is pressure, gamma is the adiabatic index, and n is the Mach number. So these are the equations that we input into Wombat for upstream and downstream to get the jump shock conditions, and that's what produces, it tells it how to produce the shock. And we put in a Mach number, where the Mach number is determined by upstream and downstream conditions. So, just recently, my collaborators at Gilles Ferrand and Summers at the Harvard University of Manitoba and their collaborator Andrew Rochelle did some synthetic maps of cosmic ray acceleration in the young type 1A supernova remnant. So they did 3D hydrodynamical supernova remnant simulations with nonlinear acceleration models. They performed the first realistic simulations of synthetic X-ray SNR emission maps and spectra. And they found that the shock wave positions in Tycho's supernova remnant implies the presence of ions. So you remember the picture I showed of Tycho before? Well, these are synthetic maps of the simulating Tycho supernova remnant. And the off is with the cosmic ray back direction turned off. So the pressure of the cosmic ray is turned off. And this is the shock front. And you can see there's a difference between the shock front's position when the cosmic ray back direction is turned off versus on. And here's a press release. So they found that the X-ray emission is decreased when the particle back direction is turned on. The model that they used is that the cosmic ray acceleration absorbs 20% of the explosion of kinetic energy. The cosmic ray acceleration affects the supernova remnant morphology, and the ejected structures are changed by the cosmic ray back reaction. They found that the shock material temperature is reduced, and that efficient particle acceleration could possibly occur at reverse shocks. So this is what they will be doing in the future, is exploring whether or not reverse shocks also have efficient particle acceleration. So their next step is to compare their synthetic maps to observations. And we would, in our work, we would also like to compare our theoretical work on non-Bohm diffusion to observations. The observations would be in X-ray, gamma ray, radio, and planning for Aster H. So my collaborator, Professor Somersault Harb, is a member of Aster H. And we want to look at broadband X-ray and gamma ray spectrum to constrain models for practical quantum acceleration. So the different observatories which we hope to compare our theories to are Exton and Newton, which was launched in 1999 and was ASA's X-ray multi-lunar satellite. And Exton and Newton shows evidence for cosmic ray acceleration. Chandra, which was launched in 1999, which is NASA's X-ray observatory, which also shows evidence for cosmic ray acceleration to the few hundred CeV. Suzaku, which is launched in 2005 and is Japanese X-ray observatory, which explores X-rays to gamma rays. And Aster H, which is planned for 2014 by the Japanese Aerospace Exploration Agency, which would explore between X-rays to gamma rays. So now I'll go into the second part of my talk, which is WOMBAT, which stands for Swift Objects for MHD based on TBD. So TBD is total variation diminishing. It's an efficient code in Fortran ID, which solves a variety of astrophysical MHD problems. It can actually simulate a supernova remnant explosion in 3D. It can simulate cooling from radiation. It can use passive cosmic rays, which means that the cosmic rays follows and affects the flow rather than affects the flow. And it can study diffusive shock acceleration of cosmic rays. So WOMBAT uses a hybrid message passaging interface and open multiprocessor framework. So it takes the best of both worlds for the parallelization. The part that I'm using, the diffusive shock acceleration module, is actually not parallelized, so I'm not working with that. The other modules are parallelized. It can deal with weak and strong scaling up to at least 8192 cores, and uses a finite second order finite differencing scheme on an Eulerian grid. It uses TBD and a word type Riemann solver. So I must admit, most of WOMBAT is a bit of a black box for me. It's a very massive code, and it's been a challenge for me using that code. And hopefully I'll be editing more of it later. But more on the solver, you can take the ideal MHD equations and reduce them to this form equation. Q is a state vector, F is a thrust function, and you have a Jacobian matrix given by df to q. The first step that WOMBAT does is it gets the eigenvalues of the Jacobian A, and then it uses a nonlinear Riemann solver. It assumes two adjacent states evolve into a set of uniform states separated by left and right-hand shocks and rarefactions. It uses initial guesses and then iterates those guesses towards the jump condition. So this is a diffusive convection equation. And the diffusive shock acceleration part of WOMBAT is 1D with physics from other dimensions. So the magnetic fields can be in more dimensions. It's considered 1.5D. And F is its cosmic ray distribution function. U is the bulk force speed. Kappa is a spatial diffusion function. So this is the part that I've been working with, is editing kappa and seeing the effects of the acceleration of particles on it. D is the momentum diffusion coefficient, which is assumed to be 0. S is a represented source term, so that has to do with the injection flux, the fraction of cosmic rays, the fraction of particles between cosmic rays. And of course, the cosmic ray inertia is ignored because this is a small mass function. So what does the diffusive shock acceleration module actually do? It doesn't solve for F, it solves for G, which is F times P to the 4th. We'll be coming to this later. And it also solves for N, which is F P to the 3, where P is momentum. So it sends N and G into the diffusive convective equation, and we can construct F from N and G. So observations indicate that this Q is equal to 4.2, F is proportional to Q minus P. So when we get our plots of our results, we want to Q at 4.2 to see if shows the observations. So the inputs of the diffusive shock acceleration module are the cosmic ray feedback, whether or not it back reacts, the cosmic ray electron energy losses, which are due to synchrotron inverse Compton, the cosmic ray species, whether or not they're electrons or protons, the minimum and maximum momentum and thinning, the cosmic ray injection fraction, the ratio of the perpendicular and parallel diffusion coefficients, and the Bohm-like diffusion parameters. But this can also be edited to be either Bohm or some other model. So our problem is the ratio of the perpendicular to the parallel diffusion coefficient, and we've been setting it equal to 1. However, in the future, we want to explore that and explore the effect of the geometry on the acceleration. So in the toy model that I'll be talking about, we use parallel diffusion, where there's parallel shocks, between the shock and the magnetic field are both in the same direction. In the physical model that I'll be discussing, it uses perpendicular diffusion, where you have perpendicular shocks, where the shock is in one direction and the magnetic field is different. So just a brief review of diffusion. Diffusion occurs obviously in lots of natural sciences. Even in neurobiology, you have diffusion, obviously, and this is a diffusion equation with the proportionality constant kappa is the diffusion coefficient. The units of the diffusion coefficient are distance of my squared over time. And the diffusion length is given by this quantity, where us is the velocity, because the diffusion coefficient is the diffusion length. And then the diffusion time scale is given by kappa and the squared. So the standard assumption is the Bohm limit. The Bohm limit assumes that the mean free path is a 1 radius, which is given by p over 2 times p naught, which we get just from the Lorentz force and circular motion. So you have your magnetic field, you have a particle spiraling around it, and you calculate this system, so the gyro radius, or the 1 radius. The assumption in the Bohm assumption is that it gives the minimum diffusion coefficient for parallel and the maximum perpendicular diffusion coefficient, and then you have isotropic diffusion kind of equal to each other. However, I think it's in the solar wind community, there's some indication that you get maximum acceleration energies per perpendicular diffusion coefficient, which is less than the Bohm diffusion. So when your diffusion coefficient is less, you get much more acceleration energies because it can collide more and the interactions can accelerate the particles. So Bohm diffusion is typically used, but it is not rigorously derived in most cases. In one case, it was rigorously derived analytically when the turbulent component in the magnetic field is greater than the mean magnetic field. But there's a lot of discussion on this. There have been some questions about whether or not it is valid in a nonlinear regime. And there are some questions about if you change the shock geometry, can you lower the diffusion coefficient? So a parallel shock is where the magnetic field and the shock are in the same direction. So this is a Supernova Remnant cartoon. The shock is going outward. And you have a perpendicular shock, and the magnetic field is perpendicular to the shock. So now let's talk about shock geometry. Are shocks with perpendicular, parallel, or oblique orientations in the magnetic field more efficient at cosmic ray acceleration? This is another topic of a lot of discussion. And Jagruti in 1987 did numerical studies which showed that perpendicular shocks would be more efficient. However, some analytical studies by Emil Shachi showed that oblique shocks might be more efficient. So there's just a lot of discussion about whether or not what shock geometry is more efficient at cosmic ray acceleration. Bohm diffusion is usually applied. As I said before, it is not usually rigorously derived. And some people have found that it fails in strong turbulence field. And also, does a helical path even make sense when you have strong turbulence? So if this is the mean magnetic field, this is is a turbulent component. Does it make sense to have a long-run radius when you have turbulence? So here you can get a derivation of Bohm diffusion. It just comes from the relationship between the parallel mean-free path and the diffusion coefficient and the definitions of momentum and relativistic energy. And then you put it all together, you get that the parallel mean-free path can be reduced to the one radius. And this would give the diffusion. So this is the assumption is that the minimum mean-free path is the one radius and the minimum diffusion coefficient, which gives you maximum energy. So this is in code units, which I'm calling PC. You get, when you put all the constants together, you get this for the Bohm diffusion coefficient. It's computationally difficult to look at Bohm diffusion, so often people look at Bohm-like assumption for the isotropic diffusion coefficient, which is written by this equation, they call it constant p to alpha. And here are some plots of the isotropic diffusion coefficient for Bohm-like. The magenta is where alpha equals 1, so it's alpha. The Bohm is relativistic, and this is Bohm relativistic. The blue is for alpha 0.5, and you get alpha 2, you would get non-relativistic. So now we'll talk about a non-Bohm coefficient model. There's some thought that if the parallel mean-free path is greater than the correlation length of turbulence, that you would get an isotropic scattering, which means that you wouldn't have isotropic diffusion. And the non-Bohm model at high energies agrees with computer simulations and analytical work of the long random walk studies. At high energies, these studies indicate that you expect the diffusion coefficient to level out. So instead of getting a diffusion coefficient that increases with momentum, these studies indicate that maybe the diffusion coefficient should level out with momentum. So based on this...
Do you have a qualitative explanation of why that is? Right, because the field lines are random walking with a gyro radius or something like that. And the Bohm random walk step is the gyro radius?
I have to kind of talk to you about that later.
Okay.
So this is a model, this model would give you this plotting of this asymptote and the diffusion coefficient. And these are just very preliminary guesses of what you could have for the characteristic momentum and the diffusion coefficient. And you might be changing these values. Basically, we're going to be looking at different characteristic momenta, different kappa knots, and different alpha. And I did a parameter survey of those to see what the diffusion coefficient looks like, and whether or not you can accelerate the particle in a reasonable time frame. And LC is a correlation.
So correlation line of turbulence, because I know that turbulence has a wide range of scale, from large scale to small scale. So what is the correlation line of turbulence here? Small scale, large scale?
So we're guessing it's sort of around like a parsec.
So the outer scale.
Yeah, it's a. But as I said, there's a lot of different, I didn't say this, but there's a lot of different papers about what the correlation of turbulence would be. And some of the guesses that we've been thinking about have been disagreeing with each other.
So I would imagine this is a microphysical process, right? So this would be the actual field line random walking on small scales.
So, for the toy model, I looked at Bohm-like, which is kappa is equal to kappa naught to alpha, and kappa naught, which is constant unstable coordinates. In non-Bohm, using this formula, and kappa naught is constant stable coordinates. And for the realistic models, we're using realistic ISM inputs, and the Bohm we're using Bohm rather than Bohm-like, although we're going to be exploring Bohm-like as well. And we're also exploring Non-Bohm. So for the toy model, this is a toy model of the little g that I showed you before, which is related to F4. The horizontal axis is position, and the vertical axis is momentum. So the particle comes in, this is the unshocked region, this is the shocked region. And it hits the shock, and it diffuses into the higher momentum. So this is a phase-space image. And for different parameters, for the Bohm, like in the Non-Bohm, I got these different phase-space images. So we found the model strongly affects the phase-space image of the shock. For the integrated spectrums, this is the integral of little g over space versus the log of the momentum. We did a study on the toy model for Bohm-like and Non-Bohm models and different parameters. So you can see the Bohm-like, this is cutoff, this break in the spectrum, which is what you observe. Since this is the momentum, if you want to see whether or not something has the slope that matches the observations, and the slope should be minus 0.2, you want the cutoff as well. So for the different models of the Non-Bohm, they do not accelerate to higher energies or higher momentum than the Bohm. So the red is an alpha 0.51, kappa naught is 1, and the KC value is 1. The green, the blue, the yellow, and the cyan are all Non-Bohm model. So you see that the Bohm-like matches the parallel observations to get the slope as expected. And the higher maximum accelerated energies changes with the model. So we can see that the diffusion coefficient does affect how high the momentum can reach. And some studies have, a lot of studies have been done on this. Colin Jones in 1991 explored this as well. And we found that the question is, can Non-Bohm give a higher acceleration energy? So using more parameters, we find that the Non-Bohm, so this black is not Bohm-like, and this reaches higher momentum than the Bohm-like models. These are different Bohm-like models for different parameters. So the maximum acceleration energy changes with the model. This one, this Non-Bohm model does match parallel observations, but you're not getting the cutoff, which is something that worries me. And does the Non-Bohm give higher acceleration energies needs to be explored with the physical model. So just looking at some time sequence, some results from the toy model. For the Bohm-like and the Bohm, you do get the sanity check, you do get the jump shock conditions and satisfied, you do get the jump in density. And there's some thickness, there's a dot here, so there's some thickness to the shock. So this is the upstream or unshocked, and then it goes to the shock, and it's increase in density. There's an increase in pressure as well as expected, and this also is for the Non-Bohm models. And the velocity also has the expected jump. So now I'll talk about the current work, or the physical model. We're using a Mach of 30. You would expect the Mach number to be higher for Supernova Remnants, then you get two computational challenges. And as long as you have a strong shock, which you do have at a Mach of 30, once you have a strong shock, then most of the physics is pretty accurate. We're exploring different densities. If you have an area of sort of star formation regions, you can get even higher densities. So we're finding that the density affects the model pretty strongly, as well as the magnetic field. And 3 microgauss sort of as a background for the ionosphere is a bit low, and you could boost the magnetic field in some areas as well. So we're exploring the lower density and magnetic field as a result. And the velocity we compute from the sound speed and the Mach number, and for the pre-shock condition, it's going to be thousands of kilometers per second. The pressure we're exploring, how that affects the physics too. assumption. For the post-shock conditions, we're using the jump shock conditions and the magnetic compression, which is the same as density compression. So one of the computational challenges is you have to be able to accelerate the particle to the maximum momentum within a reasonable time frame of a supernova remnant phase. So from Jury 1983, there's an equation for the time to acceleration for the unshocked velocity, shock velocity, this is shock velocity, including injection momentum, this is the maximum momentum, so we want to use around the mean, or 10 to the 15 eV for this. And then you have the upstream diffusion coefficient and the downstream diffusion coefficient. So you can kind of see this makes sense just from dimensional analysis. The diffusion coefficient divided by velocity squared for two direct dimensions. And people have found it to be accurate once you derive it analytically as well. So for Bohm diffusion, which once again is this, you get time to accelerate to the maximum momentum given by this equation. For a non-Bohm model, using this as the diffusion coefficient, and your time to accelerate to the maximum momentum is given by this equation, F1 is that of the geometric function. So you can study the non-Bohm diffusion time to maximum acceleration in different regimes to get an idea of how it behaves. So you can divide it into the upstream unshocked and the downstream shocked region. And where I would be either 1 or 2, you can explore in a regime where the characteristic momentum is less than the injection momentum, the regime where the characteristic momentum is between the injection momentum and the maximum momentum, where the characteristic momentum is greater than the maximum momentum. So it's really a challenge to see, to get these values within reasonable time frames, because for a lot of the values, to reach the mean, you would need like many hundreds of thousands of years, which is not realistic even within the third phase of a supernova remnant. So we're changing the input parameters, adjusting those, and that changes the time to maximum acceleration. So here are just some plots of the diffusion coefficient for our model versus the Bohm model for different values of the parameters. So in this case, for these sets of parameters, our model is less than the Bohm model. So in these regions of this is the momentum mass of the photon times the speed of light. So for these momenta, it's less than the Bohm diffusion. So you would expect we would be able to accelerate to higher energies in the Bohm diffusion model. In this model, for this use of parameters, we would expect we would not be able to accelerate to higher energies. And for these parameters, we would expect, again, that our model would be successful in accelerating to higher energies. So there's some computational challenges related to this work. One is resolution. For different momenta regimes, you need either higher resolution or lower resolution, and we don't have adaptive mesh refinement incorporated into Wombat, so we need to emulate that, and in order to be able to resolve everything. Also, the box size needs to contain several diffusion lengths, and at high momentum, when you're looking at the mean, it's very large. So there's some resolution issues with the program. Then another computational problem is the acceleration time to the mean is too long for most choices of parameters. So we're studying the parameter space for different densities, magnetic field, and parameters of the diffusion coefficient. So we're looking for reasonable time frames. We're also looking at Bohm model versus Bohm light. The Bohm model is more computationally intensive, and we want to find realistic physical parameters for our model. So a summary of current work is we're developing Wombat to explore more realistic diffusion coefficients. detective shock geometry, and cosmic ray acceleration. We implemented Bohm and non-Bohm models for a toy model in which the non-Bohm model with parameters might be able to accelerate cosmic rays to higher maximum energies than some Bohm models. And the physical model working very hard on, and that needs some work. So the takeaway message is that cosmic ray acceleration depends on the diffusion coefficient. Bohm diffusion is an assumption. The question is, could other models accelerate cosmic rays to higher energies? And more work is needed. So for future work, we want to explore the physical model and change the different parameters. We want to incorporate cosmic ray feedback, change the injection fraction, study the impact of the turbulent magnetic field. So it's currently assuming the turbulence exponent scale, so it's one that assumes. We'd also like to explore magnetic field amplification or the relative instabilities, which seem to be very important to accelerating cosmic rays. I want to explore the role of shock geometry, which types of shocks are more efficient, and try different diffusion coefficient models, and also do a comparison of models with observations. So thank you very much.
You showed the cosmic ray spectrum, and it has an E. Several years ago, there was a discussion that there might be also an angle. What is the situation about this one?
Oh, well, this one?
Yep.
So, you're asking about the region angle. So, what is your question?
Yeah, what is now the situation? Is this a real feature of the spectrum, or?
I thought so.
Yeah.
It's my impression that it's sort of.
I have a question. So in the conclusion, you mentioned that you plan to compare with observation.
Right.
So how should you proceed?
So we'd like to look at the integrated spectrum and compare that with observation.
So the spectrum of cosmic rays.
Right.
Okay, so we plan to coordinate with the speaker, and we will meet in front of the later at 6. So if anyone wants to join us, please. Okay, so that's how you